Hello everyone. Our project focuses on the customer assignment problem, modeled as a minimum cost network flow with additional binary variables. This problem is inspired by real-world facility planning. In many industries, we need to decide where to locate facilities and how to assign customers to them in the most efficient way. For example, a company may decide which warehouse serves each retail region, or a hospital network may assign patients to nearby clinics. These decisions strongly affect both service quality and cost, so optimization models like MC and F can help make them smarter and more systematic. The customer assignment problem is closely related to the classic facility location problem. The goal is to minimize the total weighted distance between customers and facilities. When the number of customers is large, we use k-means clustering to group them into a few representative clusters. Each cluster is represented by a centroid and assigned to one facility. The diagram on the right shows this relationship. Blue points are clusters and red points are candidate facilities. To make our model clear and consistent, we define standard names for variables and parameters. These parameter settings follow Groby's customer assignment notebook. We also make several simplifying assumptions to focus on the core logic. Each cluster must be assigned to one open facility. Facilities have unlimited capacity. Costs are linear and proportional to wait times distance. Distances are Euclidean, and offloads are integral, meaning each cluster sends one unit of flow to its assigned facility. Finally, there are no flows between clusters, only from cluster to facility. Based on these settings, we build the model in two stages. First, we use PULP to solve a binary integer programming model that decides which facilities should be opened and how clusters are assigned. Then, using Network X, we solve the minimum cost network flow version after the binary decisions are fixed. Mathematically, our model starts as a binary integer program, or BIP. The objective is to minimize the total cost, which is the sum of each cluster's weight multiplied by its distance to the assigned facility. We have a limit on the number of open facilities, represented by the constraint on the sum of the select J variables. Once these binary decisions are fixed, meaning we already know which facilities are open, the problem simplifies into a pure minimum cost network flow model. In this form, the binary variables disappear. This allows us to interpret the same problem from both a combinatorial and a flow network perspective. That concludes the setup part. Next, my teammate will show how we implemented this in PULP and later compared it with the Network X solution.
Now, let's come to the PULP part. First, I'd like to introduce the setup of our model. To ensure reproducibility, we set a random seed to 10101. Then, we specify several key parameters for the model. For example, we generate 50,000 customers, 20 candidate facilities, and allow at most 8 facilities to be opened. In our model, customer locations are generated from Gauss distributions centered on randomly selected population hubs, whereas facility candidates are placed uniformly at random. The model's dimensionality is reduced by clustering individual customers with the k-means method from sklearn and optimization is then performed on these cluster representatives.
Hello everyone. In this part, I will introduce how we applied our model using PULP. First, we started by computing the distances between clusters and facility candidates. This step allowed us to understand how far each cluster of customers was from potential facility locations. Next, to make the optimization more efficient, we restricted the feasible connections to the closest 99%. That means we only kept realistic and nearby connections, eliminating very long or impractical distances. After that, we formulated a mixed integer linear optimization model in PULP. The goal was to select which facilities should be opened and how to assign each customer cluster to one of these facilities, while minimizing the total weighted distance. Finally, we solved the model to find the optimal combination of facility location and cluster assignment that give us the best trade-off between cost and coverage. Now let's look at the results. Our optimization model achieved an optimal solution with a total weighted distance, or objective value, of about 632,000.7. The solver finished very quickly. It took only 1.33 seconds to find the solution. In this optimal solution, the model selected 8 facilities out of 20 candidates, which together solve 50 clusters of customers. We also applied a cutoff distance of 100.75, ensuring that only clusters close enough to a facility were assigned. This helped prevent unrealistic or inefficient connections. On the right, you can see the facility cluster assignment map. The pink dots represent customers, the red points are the cluster centers, and the green point are the candidate facilities. The connecting lines show how each cluster is linked to its assigned facility. So we can see the selected facilities are well distributed across the regions, effectively serving nearby clusters while minimizing travel distance. Thank you.
Now I'll introduce the part implemented with Network C, where we formulated the problem as a minimum cost network flow model. After obtaining the optimal facility locations from PULP, we fixed these facilities and reformulated the problem in a flow network. In this network, each customer cluster is a supply node. Each open facility is a transshipment node, and all flows in at a single sink. The cost on each edge equals the cluster's weight multiplied by its distance to the facility, representing transportation cost. The network contains 59 nodes and 407 edges, including the 8 open facilities selected by PULP. We solved this model using the network simplex algorithm of Network C, which is highly efficient for large networks. The results show all 50 clusters were assigned and the runtime was much faster than PULP. The model achieved an objective value, and recomputing the total weighted distance perfectly matched PULP's result. Next, we visualize the assignment results. Gray points represent customers, blue dots are cluster centers, red triangles are facilities, and green lines show assignments. Each cluster is assigned to exactly one facility, and the spatial distribution covers all regions efficiently. In terms of facility utilization, Facility 18 has the highest load, followed by Facility 17 and Facility 6. Remaining facilities serve few clusters, and the workload distribution is balanced with no congestion. To further verify, we recalculated the total weighted cost, which again matches PULP's outcome. For example, cluster 0 is assigned to Facility 18, confirming that the network X model reproduces the same objective and assignment structure. Overall, the network C model demonstrates outstanding computational efficiency while achieving identical results to the integer programming model. It independently verifies the PULP solution and highlights the effectiveness of graph-based methods in large-scale optimization.
Now I will present our comparison analysis between PULP and network C implementations. On the left is our comparison table. PULP uses binary integer programming with 1010 binary variables, solving in 0.077 seconds. Network C uses minimum cost networks flow, solving in just 0.0054 seconds. The key findings is that network C is 14.31 times faster. This is due to its specialized network's simplex algorithm, no integer variables, and reduced problem size. Although objective values differ, both methods produce 100% identical cluster to facility assignments, confirming solution correctness. In practice, PULP handles strategy facility allocation decisions, while network C provides rapid tactical optimization. Together, they form an efficient two-stage framework. Now let's examine our first sensitive analysis on the max facilities parameters. We test the values from k plus 3 to k plus 15. When k plus 3, the cost is 917,729. At our baseline k plus 8, the cost drops. The minimum is reached at k plus 12. The total improvement is 32.1%, which is significant. However, the key insight is diminishing marginal returns. When k increases from 3 to 4, we save 153,215, the largest benefit. But from 9 to 10, we only saved 1,661. Beyond k plus 12, there is no improvement. This confirms that k plus 8 is an excellent balance between cost and complexity. Our second sensitive analysis tests the robustness to cost variations. We simulated scenarios with plus or minus 20% cost perturbations, 9 test cases in total. The results are excellent. Across all 9 scenarios, the facility selection remained 100% unchanged. The facility stays constant in every case. This gives us a highly robust rating. In conclusion, our combined PULP network C approach is efficient. K plus 8 is optimal, and our solution demonstrates perfect stability under cost variations, making it ready for real-world deployment.
Okay, so let's move on to the analysis part. First is LP relaxations of our customer assignment problems. Here, relax the integer constraints to allow the decision variables to take continuous values between 0 and 1. And object remains the same to minimize the total weighted distance between customer clusters and selected facilities. And we also maintain 2 main constraints. Each cluster must still be assigned to exactly 1 facilities, and the total number of the open facilities cannot exceed the predefined max facilities value.
And after solving the relax problems, the minimized total weighted distance is 623,675.71. Since this is LP relaxations of our original integer programs, the value serves as the lower bound of the integer assignment problems. On the right, the heat map shows the functional assignment values between cluster facilities. Darker shaded indicates the higher assignment proportional close to 1. We observe that many assignments are partially distributed across multiple facilities. Below the heat map, the bar chart summarizes the total assignment load per facilities. We can see that certain facilities, especially those towards the right end of the index, carry heavier assignment weights, indicate they are more cost-efficient locations in the relaxed solutions. And here we relax the integer constraints and analyze the real values of the LP relaxations. The max facilities constraint has a real value of 0, suggesting the facility limits is not tight. The assigned exactly one constraint shows a wide range of real values from up 900 up to over 33,000, representing different assignment pressures across the clusters. We also find a strong positive correlations between cluster weights and real values, which means heavier cluster exerts higher pressures on the optimizations, and it shows on the scatter plot. And here we verify the optimality of the PLP solutions. First, the solver itself turned optimal status, which means it found a certified optimal solutions. Then we conduct manual verifications, checking primal feasibilities, drill consistency, and complementary slackness. The result shows on the right, and it shows all constraints are satisfied. The optimality gap is only about 1.3%, and the compute and reported objectives match exactly. Therefore, both the solver certificate and our self-verification confirm that the solution is probable and probable optimal. And here we use Network X to verify the feasibility of the solution obtained earlier. And the checks including whether all clusters are assigned, whether each assignment represents the feasibility mask, whether how flow balance is satisfied, and whether the facility's usage stays within the limits of the 8 facilities. All these conditions are satisfied, so the solution passes the feasibility test. However, unlike PLP and Network X does not provide a solver certificate of dual information, so it cannot formally prove optimality. Its algorithms, like the minimum closed flow, are designed to find optimal solutions under given constraints, but without a certificate, we can only treat it as a practical verification tool rather than a formal proof. So in summary, PLP confirms optimality, and while Network X confirms feasibilities and consistency of the obtained solutions. That's all of my part.
At last, let me conclude what we have got from the work we have done. Firstly, let's see about the comparison between PLP and Network X. PLP builds clear mathematical models with dual values and proofs, where Network X is algorithmic, emphasizing speed and graph structure. In short, PLP focuses on theory and the Network X on efficiency. In performance, PLP took about 1.3 seconds with full analysis, when Network X finished in 0.008 seconds, much faster. Simply put, PLP is slower but smarter. Network X is faster but lighter. And about realization and sensitivity. Realization showed little change, meaning the model was already near optimal. Sensitivity analysis proved it's stable. Key facilities matter, but assignments stay consistent even with cost changes. Our solution is proven optimal. Primo equals dual and the solver confirms it. The PLP result is accurate, stable, and verified. In summary, POLP gives deep insights and proofs, while Network X gives speed. And we can consider hybrid approaches in real-life applications.